Right, so suppose that we want to find the area of a region that is bounded above the curve y is equal to uh, f of x, below by the curve y is equal to g of x, and on the left and right by the lines x is equal to a and x is equal to b. So we have a function y is equal to f of x. So that region is bounded by this y is equal to f of x, and below that region, it's bounded by the curve y is equal to g of x. And on its sides, it's bounded by x is equal to a and x is equal to b. So we have this region here between the two curves, f and g. What we're looking at is that region there. And what we're saying is that above that region, there's this function f that bounds it, and beneath it is the function g, which bounds it. And then looking at its sides, we're going to see that there's x is equal to a, which bounds it there. That's a straight line. X is equal to a, and x is equal to b. All right, so it's bounded above, beneath, to the left, and to the right. The region might accidentally have a shape whose area we will find with geometry, right? Such as us looking at the area of a rectangle. But if f and g are arbitrary continuous functions, we usually have to find the area by computing an integral. So let's consider the rectangle that we're given here. These coordinate points we have here, we have ck, and that's the x point. To find the corresponding y point, we'll have to sub in ck in f. So that gets us f of c of k. And for the function beneath, we have ck and g c of k. And the height of this rectangle here is simply going to be f c of k minus g c of k. This defines the height here, and then the length is given by the change xk here, meaning that the area of this rectangle here is given by its length here multiplied by that height f minus g at the point ck. So the area delta ak of the k rectangle is the product of its length, right? F c of k minus g c of k, and its width or length delta xk. So what we did here was that instead of considering this entire region, what we did was to partition a small section of that bounded region, and we found the area to be delta xk multiplied by fck minus gck. So we have our definition here. If f and g are continuous functions, which we can see they are, these are just examples. Right, so if they are continuous functions with f greater than or equal to g throughout the closed interval a and b, then the area of the region between the two curves y is equal to f of x and y is equal to g of x from a to b is the integral of f minus g from a to b, with the area being equal to the integral of f of x minus g of x dx from a to b. So that's the idea here is similar to the rectangle that we consider. But instead of just having one rectangle, we have infinitesimal number of rectangles that we work out, right, based on the integral. You have looked at the application of the integral before, right, as a method for finding the area under a curve. So now let's take an example. Does anybody have any questions on this? No questions. Our example one here, we want to find the area. Between two curves. So we want to find the area of the region which is bounded above by the curve y is equal to a to the, so it's 2 a to the minus x plus x below by the curve y is equal to a to the x divided by 2, and on the left by x is equal to 0 and by x is equal to 1. So with our first example, it says to find the area of the region bounded above by the curve y is equal to 2 e to the minus x plus x. All right, so this is the region above, this is the curve above, right? That's f, and it's also bounded below by the curve y is equal to e to the x divided by 2. And it's also bounded on the left side by x is equal to 0, and on the right side by x is equal to 1. Right, so a good way of thinking about this first before you do any calculations is to, if you can, right, try to imagine what they'd look like. Right, and we do that with the help of Desmos. So the two curves that we're given are y is equal to 2 to the e minus x plus x, and y is equal to 1/2 a to the x. And we're told that the region is bounded on the left side as well by x is equal to 0 with this green function. And on the right side by x is equal to 1. Right, so the upper bound here, the function that's bounding the curve, this is 2 e to the minus x plus x, the one in red. And then the blue function bounds it beneath. It bounds this region here, which is 1/2 e to the multiplied by e to the x. And then on the left side, it's bounded by x is equal to 0. And on the right side, it's bounded by x is equal to 1. Right, so this is Desmos.com. You can use it to visualize your curves. Right, so the region we're interested in here is this region here, which is bounded by these curves. right? So the area, what we're looking for here is that region. So let's take that. So the examples that you've been doing so far, right, with right, this was a simple two-dimensional shape where you found the area to be pi r squared. Right? So imagine want to now take the same idea, but now extend it to more complex shapes, such as this one here. So instead of us having a circle that we want to find the area of, this is this region that we can carve out right there. Something like that. You can draw it better on. So that's the area that this region, right? That's the one that's bounded. That's what we want to find the area of inside here. So the curves here bounding the function on beneath and above it, that's going to influence f and g, and then the function, curves x is equal to 0 and x is equal to 1, bounding the function on the left and right sides, that's going to inform the lower and upper bounds of the integral. So our f and g here, this is what we're looking at there, right? We consider the top function and we subtract the bottom function from that. And this here is what informs our bounds. X is equal to A, X is equal to B. So we're going from X is equal to A, X is equal to B. That's based on how the function is bounded on the left and right sides. So I'm going to keep this here for you. So our area here, this is f of x minus g of x dx. So it matters here which function is at the top and which is at the bottom. So in an exam situation or test, you're not going to have a graphing tool. The tool is only meant to help you understand what it is you're doing here. But when you're in a test, you'll be expected to manually work out which function is at the top and which is at the bottom. Right. So to get the height, you have to take the function which is at the top, and from it you subtract the function which is at the bottom. That's how we work out the height as seen here. And from there we multiply that with the width or the length. And our length here, this is that small change dx. So you can pick a small region like that. And this here, that small change in the horizontal length, that is our dx, our differential length. And then you'll take your f ck, and from it you subtract g ck, and then the differential area that is going to be made up of f ck minus g ck multiplied by dx. But now this gives you the area for this portion here. But now if you wanted to extend the same idea to account for this entire region, that's where you bring in your integral and consider your left and right upper bounds and so on. So going back to our plot, note here that the red function is on top, which means that that's our f, and then the blue function, this is at the bottom, right? Which means that to get our height, that is going to be this function here at the top minus the function at the bottom. And now let's look at how you'd work that out in a test situation. So how you will go about this is that you consider, let's take our y is equal to 2e to the minus x plus x. And we also have y is equal to a to the x divided by 2. So what you want to do here is to compare the function values for these two curves. So since we're given that we'll be going from x is equal to 0 to x is equal to 1, that is our domain. That means that we'll take the value of f of 0 and sub it in there to see what value we get. So when you sub in f of 0 in there, what you're going to end up with is 2. You can also do a table of that. We'll do that as well to show you how you will do it. So we said all right, that's the next point we can consider. F of 0.3. You sub this value in there, and that's going to give you 1.78. And f of 0.6, and sub that in there as well. And that's going to give you 1.7. And f of 0.9. Let's just round that to okay, so it's 697 p actually, and this is 1.71. And for f of 1, at f of 1, this is equal to 1.74. And then let's consider the function g. At g of 0, this is equal to 0 as well. G of 1 of 0.3. This is equal to 0.67. G of 0.6. This is 0.91. And then G of 0.9. This is 1.2. And at G of 1, this is 1.4. So as can be noted here that, so what we do is compare the output values to determine which function is at the top. So at f of 0, g of 0, we can see that this function is greater. So it's greater. And then f of 0.3 is greater than 0.67, so greater. this 1.698 is greater than 0.91, right? And 1.71 is greater than 1.2. This here is greater than 1.4. And from there, we can note that we can conclude that F is above G on 0 and 1, meaning that this function here, that's what you'd subtract from. And then if, to just show you how you will work this out with your cursor calculator, right? Can everybody just take out their cursor calculators? So what you're going to press is on. So most cursor calculators should be able to do this. So we're looking at table steps. So step 1, you press the on button. And then the second step, that you press the mode button. My calculator is 991 ES class. Oh, you're not allowed to use the calculator. All right, noted. Then in this case, you will not need the table then, but it can help you practice, just get the hang of it. Right, so if you still do have your calculator next to you, you can just follow along, and then from there, after you press mode, what follows is table. You press the number that corresponds to the table. On my calculator, like I was saying, this is 7, number 7, which is table. So on your calculator, that may be the number 3. Right, just press the corresponding number. And then from there, it's going to give you f of x. So you'll type in your function f at a time. So in our example that we had, so it's actually f of x is equal to 2. And then you type in your x over 2. And from there, you press the equal sign. And it's going to prompt you for start. So we can start from 0. We can end at 1. That we can use steps of 0.3. So we started at 0, 1 to end at 1. Our steps here, those 0.3. So when you're practicing, that's how you can go about it. Right, so we're going to lean more towards problems where you don't have to actually just sub in, but you using a calculator, you can just manually do it yourself. So we've determined here that the function, this function here is the one that's at the top, and then this one is at the bottom. And you do your comparison Right, so the area here, we're going from 0 to 1, and our top function, that was 2e to the minus x plus x minus the bottom function, which was e to the x over 2 dx. And this is 2e to the minus x plus x minus e to the x over 2 dx. So you're already familiar with the integration. So this is going to be minus 2e to the minus x plus x squared over 2 divided by 2 minus e to the x divided by 2. And we're evaluating this from 0 to 1. And this is going to be minus 2e to the minus plus minus 1 plus 1 squared divided by 2 minus e to the 1 divided by 2. And then we close that up. And this is minus 2e to the minus 0 plus 0 squared divided by 2 minus e to the 0 divided by 2. And from this here, that's going to be 0, and this is going to be 1 here. So this is 1, this is 1, 1, 1. And minus 2 e to the minus 1 plus 1 over 2 minus e over 2 minus, so this is going to be minus minus 2, which is plus 2. And then this here is minus as well, so minus minus plus 1 over 2. And quite simply, what we end up with here is 3 minus 2 divided by e minus e divided by 2. Does anybody have any questions here? Is there anything unclear? Is everybody happy? All right, just give me a thumbs up if everything's as clear to you. All right. So let's move on to the next problem. So with our second example, so once you find the area of the region enclosed by a certain parabola. And the parabola is given by y is equal to 2 minus x squared, and the line y is equal to minus x. So we're not given any left or right bounds, right? We're only told to find the area of the region which is enclosed by the parabola y is equal to minus 2x squared, and the line y is equal to minus x. So the exam approach for this one, right, is that you will consider where your two curves intersect. Right. So where they intersect is going to give you a range of values that you can then test out to see which function is at the top and which is at the bottom. So what we're missing right now is which function is at the top and which function bounds the region underneath. And also, we're missing the lower and upper bounds of the integral. So when it comes to the area, we don't know what A is, we don't know what B is, we don't know which function occupies the F position and which occupies the G position. Dx. Right, so we're going to solve this simultaneously. So we'll take our 2 minus x squared, and this is equal to minus x. Right, and this is x squared minus x minus 2. This is equal to 0. And this is going to be x minus 2 and x plus 1. This is equal to 0. So we have that x is equal to 2, or x is equal to 1, to minus 1. So that gives us the domain where these two curves intersect. Right, so our x here is an element of minus 1 and 2. So from that domain, we have to figure out which function is at the top and which is at the bottom. So how you will now go about this is that so you can take this was y is equal to 2 minus x squared. You can call it f if you want, or any other variable. For neutrality, we can call that k. And this one here we can call n of x. So we can sub in the minus 1, right? Then that's going to be 0, right? That's 2 minus 1 all squared. So 2 minus that and this is going to be so it's minus 1 all squared, which is positive. So that leaves 1 actually, not 0. So this here is going to leave us with 2. And then the next one we look at. So the steps that we're using here, we're using a step of 1. Right? To move from one number to another, we're using a step of 1. So minus 1 to 0, from 0 to 1, from 1 to 2. So k of 1 here, right, that is still going to give us a value of 1. And then k of 2, this is minus 2. And then our n of minus 1, this is 1. Our n of 0, this is 0. Our n of 1, this is minus 1. Our n of 2, this is minus 2. So remember what we said before when we were looking at the definition. We said f is greater than or equal to that function, the one that's we need. And we can see here that k of minus 1 is equal to 1, which is equal to n of minus 1. So just taking you back to the definition. We're looking at f greater than or equal to g. And from here, what we note is that k of x is greater than or equal to n of x. That 2 is greater than 0, 1 is greater than minus 1. And the minus 2 here, these two are equal to each other. But k here is greater than or equal to n. All right, so if we were to go to Desmos to look at this, so our functions here, we're looking at 2 minus x squared, which is a parabolic function as expected. And the next one, that was minus x. Right, so what we did first was to work out the 2 points where they intersect. And that was x is equal to minus 1 and x is equal to 2. Right? And we can see that if those form our bounds, and this is the region that's bounded by the two curves here, right? The function, the parabolic function is at the top, and the curve y is equal to minus x, our straight line, this is at the bottom, meaning that this is going to be 2 minus x squared minus x. Is everybody happy with that? All right, no questions. So that means that the area of the region bounded by the two curves is going to be the integral of 2 minus x squared minus x dx squared from minus 1 to 2. And this is minus 2 minus x squared plus x dx minus 1 to 2. And this is 2x minus x cubed divided by 3 plus x squared divided by 2 from minus 1 to 2. And this is 2 multiplied by 2 minus 2 cubed divided by 2 plus 2 squared divided by 2 minus 2 times minus 1 minus 1 cubed divided by 3 plus minus 1 all squared divided by 2. And this is 4. And this is 8 here divided by 2, which is 4. And this is 1 here, 4 divided by 4 minus 2. This is going to be minus minus. So it's minus 1 cubed, which is going to be minus. Right, so plus a third plus 1 over 2. And this is 1 minus right, so that's a third plus 1/2. Right, so it's just ending. So it's at x cubed. So it's x cubed divided by 3, not 2, actually. Let's just correct that. So meaning that this is going to be 8 over 3. From there, these are just simply numbers that you can work out to 9 over 2. Does anybody have any questions here? No questions.